Imagine, if you will, a time machine that can take us back to the very beginning of the universe. We can't build one, but we don't need to. The universe has given us a built-in time machine, a cosmic fossil that carries the imprint of creation itself. It's called the cosmic microwave background, and it's the oldest light in the universe. This faint glow, echoing from the dawn of time, holds the secrets of how our universe came to be. Stick around, because we're about to dive into the story of our cosmic origins, a tale written in the language of light and echoing through the vast expanse of space. The birth of the universe. The universe, in its infancy, was a seething cauldron of unimaginable heat and density. It was a place where the very fabric of reality was being woven, where particles danced in a cosmic ballet, and where the seeds of everything that would ever exist were sown. This primordial soup, often referred to as the cosmic plasma, was a hot, dense fog of particles and radiation, a far cry from the cool, sparse expanse we observe today. The universe was opaque, a place where light could not travel far before being scattered by the dense particles that filled the cosmos. As the universe expanded, it cooled. This cooling allowed for the formation of the first atoms, primarily hydrogen and helium. These atoms could not hold on to electrons, so they were ionized, meaning they had a positive charge. This ionization allowed light to travel freely for the first time, a dramatic moment known as recombination. The universe became transparent, and the light from this epoch has been traveling through space ever since, redshifted to microwave frequencies by the expansion of the universe. This ancient light, now known as the cosmic microwave background, CMB, is a snapshot of the universe when it was only about 380 years old, a veritable echo of creation. The CMB is remarkably uniform, with only tiny fluctuations in temperature. These fluctuations, observed as slight variations in the CMB's intensity, are the seeds from which the large-scale structure of the universe grew. They represent quantum fluctuations in the early universe that were stretched to cosmic scales by the rapid expansion of the universe during a period known as inflation. These fluctuations are the blueprint of the cosmos, the foundation upon which galaxies, stars, and ultimately, life itself would form. The CMB is a testament to the power of the universe's expansion, a cosmic fingerprint that provides a wealth of information about the universe's birth, evolution, and ultimate fate. Studying the CMB is like reading the universe's autobiography. It tells us about the universe's composition, its geometry, and its history. The CMB's uniformity, for instance, supports the idea that the universe underwent a period of rapid expansion known as inflation. The tiny fluctuations in the CMB's intensity provide a window into the universe's early structure formation. They also offer insights into the nature of dark matter and dark energy, the mysterious components that dominate the universe's energy density. The CMB is a goldmine of information, a cosmic echo that resonates with the story of our universe's birth and evolution. A symphony of light and matter. In the vast, dark expanse of the universe, a faint glow permeates, a relic from the earliest moments of creation. This is the cosmic microwave background, CMB, a symphony of light and matter that has traveled for over 13 billion years to reach us. It is the oldest light in the universe, a snapshot of the cosmos when it was just 380 years old, a mere infant in cosmic terms. This light, now stretched into the microwave spectrum by the expansion of the universe, carries with it a wealth of information about the birth and evolution of the cosmos. The CMB is not uniform. It has tiny fluctuations, anomalies in the temperature that are mere hundredths of a degree different from the average. These fluctuations are the seeds of the large-scale structure we see today. They are the cosmic equivalent of a musical score, each note a variation in density that would eventually grow under gravity's pull to form the galaxies, stars, and planets we see today. The CMB is a testament to the intricate dance between light and matter, a dance that began in the fiery crucible of the early universe. When we observe the CMB, we are not just looking back in time. We are also looking at the very fabric of the universe. The patterns in the CMB provide a cosmic fingerprint, a unique identifier that helps us understand the composition, shape, and destiny of the universe. It tells us about the nature of dark matter and dark energy, the mysterious components that make up most of the universe's energy density. The CMB is a cosmic symphony, a harmony of light and matter that resonates with the fundamental truths of existence. It is a reminder that we are not just observers of the universe, but participants in its ongoing evolution. The early universe, a hot, dense soup. In the beginning, the universe was a seething cauldron of hot, dense plasma, a far cry from the cold, sparse expanse we observe today. This primordial soup was a tumultuous mix of particles and radiation, a chaotic dance of energy and matter. The temperature was so high that electrons could not bind with nuclei, leaving the universe in a state of constant, energetic flux. This early universe was not the tranquil, orderly place we see now, but a roiling, dynamic environment where the fundamental forces of nature were the main actors. The density of this primordial plasma was staggering, with particles packed so tightly that they constantly collided and interacted. Photons, the particles of light, were trapped in this dense soup, unable to travel far before being scattered by the abundant electrons. This era, known as the photon epoch, was a time when the universe was opaque, a thick fog of plasma that obscured any light. The energy density was so high that even the simplest atomic nuclei, like hydrogen and helium, could not form. Instead, the universe was a hot, dense broth of quarks, electrons, and their antiparticles, all swirling in a cosmic maelstrom. The significance of this hot, dense state cannot be overstated. It was during this time that the fundamental building blocks of matter were forged. The intense heat and density provided the perfect conditions for the creation of the lightest elements. As the universe expanded and cooled, these particles began to combine, forming the first atomic nuclei. This process, known as Big Bang nucleosynthesis, was the universe's first step towards the complex structures we see today. The primordial soup was not just a chaotic mess. It was the crucible in which the ingredients for everything that followed were created. The transition from this hot, dense state to the cooler, more familiar universe we inhabit today was a gradual process. As the universe expanded, it cooled, allowing electrons to combine with nuclei and form the first atoms. This event, known as recombination, marked the end of the photon epoch and the beginning of the universe as we know it. The light that was once trapped in the primordial plasma was suddenly free to travel across the cosmos, creating the cosmic microwave background, CMB, radiation that we detect today. This faint glow, a relic from the early universe, carries with it the imprints of the hot, dense soup that once was. It is a testament to the dramatic changes that have shaped our universe over billions of years. The first few minutes. In the beginning, there was a hot, dense soup of particles and radiation, a primordial broth that set the stage for everything that followed. The first few minutes of the universe were a whirlwind of activity, a cosmic dance of creation and annihilation. Protons and neutrons collided, fused, and transformed, giving birth to the first atomic nuclei. This was the epoch of nucleosynthesis, a fleeting moment when the universe was hot and dense enough for nuclear reactions to occur. The cosmic symphony was conducted by the laws of physics, and the score was written in the language of particles and forces. The universe was a seething cauldron, a place where matter and energy were in a constant state of flux. In the first 3 minutes, the temperature dropped from an unimaginable 10·32 Kelvin to a mere billion Kelvin. This rapid cooling allowed protons and neutrons to combine, forming the nuclei of the lightest elements. Deuterium, the heavy isotope of hydrogen, was the first to appear, followed by helium-4, the most abundant element in the universe after hydrogen. Trace amounts of lithium were also forged in this cosmic furnace. These elements, born in the crucible of the early universe, would later become the building blocks of stars, planets, and life itself. The cosmic microwave background, CMB, radiation, the afterglow of creation, carries the echoes of these first few minutes. It is a snapshot of the universe when it was just 380 years old, a time when it had cooled enough for electrons to combine with nuclei, forming the first atoms. The CMB is remarkably uniform, with tiny fluctuations that betray the seeds of the large-scale structure we see today. These fluctuations, imprinted on the CMB, are the result of quantum fluctuations in the early universe, stretched to cosmic proportions by the rapid expansion of space. They are the blueprint of creation, the plan that would eventually give rise to galaxies, stars, and planets. The first few minutes of the universe were a time of rapid change and transformation. The universe was a dynamic, ever-changing landscape, a place where the laws of physics were written in the language of particles and forces. The cosmic microwave background, the afterglow of creation, carries the echoes of these first few minutes. It is a testament to the power of the early universe, a reminder of the incredible journey that has brought us to where we are today. The CMB is a window into the past, a glimpse of the universe in its infancy. It is a reminder of our cosmic origins, a connection to the first few minutes of creation, the era of nucleosynthesis. In the infant universe, a mere 100 seconds after the Big Bang, temperatures plummeted dramatically, creating a fertile ground for the formation of atomic nuclei. This period, known as the era of nucleosynthesis, was a cosmic alchemy, forging the simplest and most abundant elements that would later become the building blocks of everything we see today. Protons and neutrons, the fundamental particles of atomic nuclei, combined in a fiery dance, giving birth to isotopes of hydrogen, helium, and trace amounts of lithium. The universe, in its infancy, was a crucible of creation where the seeds of stars, planets, and life itself were sown. The process was swift and efficient, driven by the intense heat and density of the early universe. Protons, the nuclei of hydrogen atoms, fused with neutrons to form deuterium, an isotope of hydrogen. Deuterium then combined with more protons and neutrons to create helium-3 and helium-4, the most abundant elements forged during this era. The entire process was a delicate balance, with the relative abundances of these elements determined by the density of the universe and the rates of the nuclear reactions. This cosmic recipe, written in the language of nuclear physics, set the stage for the evolution of the universe. The significance of the era of nucleosynthesis cannot be overstated. It was during this time that the lightest elements were created, elements that would later become the raw materials for the formation of stars, galaxies, and planets. The helium produced during this era, for instance, makes up about 24% of the ordinary matter in the universe today. Moreover, the precise measurements of the abundances of these elements provide a powerful test of the Big Bang theory and the standard model of cosmology. Any deviations from the predicted abundances could hint at new physics beyond our current understanding. The echoes of this primordial alchemy can still be detected today. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, carries imprints of the early universe, including the era of nucleosynthesis. By studying the CMB and the abundances of the lightest elements, scientists can peer back in time, gaining insights into the conditions and processes that shaped the universe in its earliest moments. This cosmic archaeology allows us to reconstruct the story of our origins, from the fiery crucible of the early universe to the complex structures we see today. The formation of atoms. In the beginning, the universe was a scorching, dense soup of particles, a far cry from the cool, expansive cosmos we know today. About 380 years after the Big Bang, something extraordinary happened. The universe had cooled enough to allow electrons to combine with protons, forming the first atoms. These were primarily hydrogen and helium, the simplest and most abundant elements in the universe. This epoch, known as recombination, marked a significant turning point. It was when the universe became transparent for the first time, allowing light to travel freely. This light, stretched and cooled by the expansion of the universe, is what we now detect as the cosmic microwave background, CMB, radiation. The formation of atoms was a pivotal moment, setting the stage for the universe as we know it. Before recombination, the universe was a hot, dense plasma, a chaotic mix of particles where light couldn't travel far without being scattered. The formation of neutral atoms changed that. Suddenly, light could traverse the universe unimpeded. This is why the CMB is often referred to as the afterglow of the Big Bang. It's the oldest light we can see, a snapshot of the universe when it was still in its infancy. The CMB provides a wealth of information about the early universe, its composition, and its evolution. The process of atom formation wasn't uniform. Tiny fluctuations in density and temperature in the early universe led to slight variations in the CMB. These anisotropies, as they're called, are crucial. They provide clues about the distribution of matter in the early universe and the seeds of large-scale structures we see today, like galaxies and galaxy clusters. The formation of atoms also played a crucial role in the formation of these structures. Gravity could now act on the neutral matter, pulling it together to form the first stars and galaxies. Without this process, the universe might have remained a featureless expanse, devoid of the complex structures we observe today. The universe cools down. The universe, in its infancy, was a scorching inferno, a plasma soup of particles and radiation. As it expanded, it cooled, allowing for the formation of neutral atoms. This pivotal moment, around 380 years after the Big Bang, marked the birth of the cosmic microwave background, CMB, radiation. The universe had finally cooled enough for light to travel freely, untethered by the dense plasma that once filled the cosmos. This light, stretched and cooled by the expansion of the universe, is what we now detect as the CMB, a faint glow that permeates the entire cosmos, a whisper of creation itself. The CMB radiation is not uniform. It has tiny fluctuations, anomalies that tell a story of density variations in the early universe. These fluctuations are crucial, as they provided the seeds for the large-scale structure we observe today. Regions with slightly higher densities would, over time, attract more matter, eventually forming the galaxies and galaxy clusters that populate the universe. The CMB, therefore, is not just a relic of the early universe. It's a roadmap, a blueprint that reveals the universe's evolutionary path. The temperature of the CMB is remarkably uniform, averaging around 2.7 Kelvin. This uniformity is a testament to the rapid expansion of the universe during its inflationary phase, which smoothed out any initial irregularities. However, the tiny variations in temperature, around 1 part in 100, are what make the CMB so valuable. These fluctuations, detected by instruments like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, provide a wealth of information about the composition, shape, and destiny of the universe. They are the echoes of creation, the universe's first light, carrying with them the secrets of our cosmic origins. The last scattering surface. In the vast cosmic symphony, the last scattering surface is a celestial stage where light and matter parted ways, leaving an indelible echo of the early universe. This surface, a spherical boundary in space, marks the point around 380 years after the Big Bang, when the universe cooled enough for electrons to combine with protons, forming neutral hydrogen atoms. Before this, the universe was a dense, hot plasma, a chaotic soup where photons were constantly scattered by free electrons, much like sunlight dancing on the waves of a turbulent sea. The last scattering surface is the point at which the universe became transparent, allowing photons to travel freely through space, carrying with them a snapshot of the early universe. The light from this era, now stretched and cooled to microwave wavelengths, is what we detect as the cosmic microwave background, CMB, radiation. This radiation is remarkably uniform, with tiny temperature fluctuations, just parts in 100, that provide a wealth of information about the early universe. These fluctuations are the seeds of the large-scale structure we see today, the cosmic blueprint from which galaxies and galaxy clusters formed. The last scattering surface is not a physical object, but a boundary in time and space, a cosmic horizon beyond which we cannot see. It is a testament to the universe's early conditions, a fossil imprinted on the fabric of spacetime. Studying the last scattering surface is like reading the universe's autobiography, written in the language of photons. The CMB radiation carries imprints of the universe's infancy, revealing clues about its composition, geometry, and evolution. By analyzing the patterns and fluctuations in the CMB, scientists can infer the density of matter, the nature of dark matter and dark energy, and the overall shape of the universe. The last scattering surface is a cosmic time capsule, preserving the conditions of the early universe and offering a glimpse into the fundamental processes that shaped our cosmic home. It is a reminder of the universe's interconnectedness, a thread that ties the past to the present, the microscopic to the cosmic. The cosmic microwave background, CMB, discovered. In the vast, dark expanse of the cosmos, there's a faint glow, a whisper of light that has traveled for nearly 13.8 billion years. This is the cosmic microwave background, CMB, the oldest light in the universe, a relic from a time when the cosmos was hot, dense, and opaque. Its discovery was a monumental moment in astrophysics, a window into the universe's infancy. The CMB is remarkably uniform, with tiny temperature fluctuations, just a few parts in 100, that provide a snapshot of the seeds of galaxies and large-scale structures we see today. These fluctuations are crucial, as they offer insights into the universe's composition, its expansion, and the nature of dark matter and dark energy. The CMB was first detected in 1965 by Penzias and Wilson, who were working on a radio antenna at Bell Labs. They picked up a persistent noise that couldn't be attributed to any known source. This noise, a faint hum, was the CMB, the afterglow of the Big Bang. It's everywhere, filling the universe like a faint, cold fog. The temperature of this radiation is a chilly 2.725 Kelvin, just above absolute zero. This discovery was a game-changer, providing strong evidence for the Big Bang theory and reshaping our understanding of the universe's origins. The CMB is more than just a cosmic echo. It's a treasure trove of information. By studying its patterns and fluctuations, scientists can infer the universe's shape, its rate of expansion, and the density of its contents. The CMB also provides clues about the universe's composition, revealing that ordinary matter, like the stuff we're made of, makes up only about 5% of the universe. The rest is dark matter, about 27%, and dark energy, about 68%. Mysterious substances that we can't see but can infer from their gravitational effects and the CMB's patterns. This faint glow, once thought to be just noise, has become one of the most powerful tools in cosmology, helping us unravel the mysteries of the cosmos. Penzias and Wilson's accidental discovery. In the quiet hum of a New Jersey laboratory, two radio astronomers, Penzias and Wilson, were tuning their sensitive horn antenna, a relic from a discarded radar project. They were hunting for radio waves from the Milky Way, but something peculiar kept interfering with their observations. A persistent, unshakable noise, like the hiss of a poorly tuned television, permeated their data. It was omnipresent, arriving from every direction in the sky, day and night. This enigmatic signal was the first hint of something extraordinary, something that would later be recognized as the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang. Penzias and Wilson were initially baffled. They meticulously checked their equipment, even removing pigeons nesting in the antenna that had left behind a white, sticky mess. Yet, the noise persisted. They considered and ruled out urban interference and natural phenomena, leaving them with a conundrum. Meanwhile, across town, a team of physicists at Princeton University, led by Robert Dicke, were theorizing about the leftover radiation from the early universe. They predicted a faint, cold glow permeating the cosmos, a relic of the hot, dense state of the universe shortly after the Big Bang. When Penzias and Wilson heard about this theory, the pieces fell into place. Their persistent noise wasn't interference. It was the echo of creation itself. The significance of their discovery was profound. The CMB radiation is the oldest light in the universe, emitted when the universe was just 380 years old. It provides a snapshot of the universe in its infancy, a time when it was dense, hot, and opaque. As the universe expanded and cooled, the light was freed to travel through space, redshifted to microwave wavelengths by the expansion of the universe. This faint, cold glow, just 2.7 Kelvin above absolute zero, carries imprints of the early universe's conditions and has been traveling towards us for over 13 billion years. Penzias and Wilson's accidental discovery provided the first direct evidence of the Big Bang theory, revolutionizing our understanding of the universe's origin and evolution. The impact of their work rippled through the scientific community. It opened a new window into the early universe, allowing cosmologists to study the conditions and processes that shaped the cosmos. The CMB radiation's uniformity, with tiny fluctuations of about 1 part in 100, provided crucial insights into the universe's large-scale structure and the seeds of galaxy formation. Subsequent missions, like the Cosmic Background Explorer, (COBE), and the Wilkinson Microwave Anisotropy Probe, (WMAP), have mapped these fluctuations in exquisite detail, refining our understanding of the universe's age, composition, and geometry. Penzias and Wilson's accidental discovery, born from a persistent noise in a New Jersey laboratory, has become a cornerstone of modern cosmology, echoing the universe's creation story to this day. The CMB, a fossil from the early universe. The universe, in its infancy, was a hot, dense soup of particles and radiation. About 380 years after the Big Bang, something extraordinary happened. The universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. This event, known as recombination, allowed photons to travel freely through space. These photons, stretched and cooled by the expansion of the universe over billions of years, form what we now know as the cosmic microwave background, CMB. It's a fossil, a snapshot of the universe when it was still in its early stages, a mere 380 years old. The CMB is not just a relic, it's a treasure trove of information. It provides a wealth of data about the early universe, its composition, and its evolution. The CMB is remarkably uniform, with tiny temperature fluctuations, tiny but crucial. These fluctuations, measured in microkelvin, are the seeds of the large-scale structure we see today. They represent the density variations that would eventually grow, through gravity, into the galaxies and clusters of galaxies we observe in the universe now. The CMB is, quite literally, the blueprint of the cosmos. The significance of the CMB cannot be overstated. It's the oldest light we can see, a glimpse into a time when the universe was still in its infancy. By studying the CMB, scientists can test theories about the origin and evolution of the universe. It provides a critical test for the Big Bang theory, and it's one of the strongest pieces of evidence supporting it. The CMB also offers insights into the nature of dark matter and dark energy, two of the most mysterious components of the universe. In many ways, the CMB is a window into the unknown, a beacon guiding our exploration of the cosmos. The CMB's role in modern cosmology. The cosmic microwave background, CMB, is often referred to as the echo of creation, a relic from the early universe that provides a wealth of information about the cosmos. This faint radiation, discovered accidentally in 1965, permeates the entire universe and offers a snapshot of the universe when it was just 380 years old. The CMB's role in modern cosmology is nothing short of revolutionary. It serves as the backbone of our understanding of the universe's origin, composition, and eventual fate. By studying the CMB, scientists can infer the density of matter, the geometry of the universe, and even the distribution of dark matter and dark energy. One of the most significant aspects of the CMB is its uniformity. The temperature of the CMB is incredibly uniform, varying by only a few parts in a million. These tiny fluctuations, however, are crucial. They provide the seeds from which galaxies and other cosmic structures formed. By analyzing these fluctuations, cosmologists can test theories about the early universe and the processes that led to the large-scale structure we observe today. The CMB also provides a unique window into the physics of the early universe, allowing scientists to probe conditions that cannot be replicated in Earth-based laboratories. The CMB's role in modern cosmology extends beyond just understanding the early universe. It also plays a crucial role in testing fundamental theories of physics. For instance, the CMB provides evidence for the theory of cosmic inflation, which suggests that the universe underwent a period of exponential expansion in its first trillionth of a second. This theory explains many observed properties of the universe, including its large-scale homogeneity and the absence of magnetic monopoles. Without the CMB, our understanding of these fundamental aspects of the universe would be far less complete. Moreover, the CMB is a valuable tool for studying the nature of dark matter and dark energy. These mysterious components make up about 95% of the universe's energy density, yet their nature remains poorly understood. By examining the CMB's polarization patterns, scientists can infer the properties of dark matter and dark energy, shedding light on their roles in the universe's evolution. The CMB also provides a way to measure the Hubble constant, the rate at which the universe is expanding, which is crucial for understanding the universe's ultimate fate. In essence, the CMB is a goldmine of cosmological information, continually revealing new insights about the universe and our place within it. The CMB and the Big Bang Theory. The universe, in its infancy, was a scorching, dense soup of particles and radiation. As it expanded and cooled, a profound shift occurred around 380 years after the Big Bang. Electrons and protons combined to form neutral hydrogen atoms, allowing photons to travel freely. This release of light, now stretched and cooled by the universe's expansion, is what we detect today as the cosmic microwave background, CMB. It's the oldest light in the universe, a faint glow that permeates every corner of the cosmos, a whisper from the dawn of time. The CMB is a critical piece of evidence supporting the Big Bang Theory. It provides a snapshot of the universe when it was still in its infancy, offering a wealth of information about its composition, shape, and destiny. The CMB's existence was first predicted by Ralph Alpher, Hans Bethe, and George Gamow in 1948, but it wasn't until 1965 that Arno Penzias and Robert Wilson accidentally discovered it while working on a radio antenna. This serendipitous finding opened a new window into the early universe, allowing scientists to study the conditions that prevailed just 380 years after the Big Bang. The CMB is remarkably uniform, with a temperature of about 2.725 Kelvin, varying by only a few parts in 100. These tiny fluctuations, detected by satellites like COBE, WMAP, and Planck, are the seeds from which galaxies and galaxy clusters would eventually form. They are the result of quantum fluctuations in the early universe, stretched and amplified by cosmic inflation. By studying these fluctuations, scientists can infer the density of matter and dark matter, the nature of dark energy, and the curvature of the universe. The CMB, in essence, is a cosmic fossil, a relic of the early universe that holds clues to its evolution and ultimate fate. The CMB's temperature and uniformity. The universe, in its infancy, was a scorching cauldron of plasma and radiation. Fast forward to today, and we can still detect the afterglow of that primordial fire, known as the cosmic microwave background, CMB. This relic radiation, permeating every corner of the cosmos, carries with it a temperature of approximately 2.725 Kelvin, a chilling whisper of the universe's early days. This temperature is remarkably uniform, with fluctuations amounting to only a few parts in 100. Such minuscule variations might seem insignificant, but they are the seeds from which galaxies, stars, and ultimately, life itself would emerge. The uniformity of the CMB is a testament to the rapid expansion of the early universe, a period known as inflation. During this fleeting moment, the universe expanded faster than the speed of light, smoothing out any initial irregularities. This process ensured that the temperature of the CMB is nearly the same in all directions, a property known as isotropy. However, the CMB is not perfectly uniform. Tiny anisotropies, or directional variations, exist and provide a wealth of information about the universe's composition, structure, and evolution. These fluctuations, though small, are crucial for understanding the large-scale structure of the cosmos. The temperature of the CMB is not just a relic of the past. It is a dynamic entity that interacts with the universe around it. As the universe expands, the CMB cools, its wavelength stretching with the fabric of space itself. This redshift effect is a direct consequence of the universe's expansion and provides a cosmic yardstick for measuring its growth. Moreover, the CMB is not just a passive observer. It plays an active role in shaping the universe, influencing the formation of galaxies and the distribution of matter. By studying the CMB's temperature and uniformity, scientists gain insights into the fundamental forces and particles that govern the cosmos. The CMB's tiny fluctuations. The cosmic microwave background, CMB, is often described as the afterglow of the Big Bang, a faint echo of creation that permeates the entire universe. Within this ancient light, tiny fluctuations hold the key to understanding the universe's origins and its eventual structure. These fluctuations, minuscule variations in temperature and density, are the seeds from which galaxies, stars, and planets grew. They are the cosmic blueprint, imprinted on the sky, revealing the universe's infancy with remarkable clarity. The CMB's fluctuations are incredibly subtle, with temperature variations of only about 0.2 degrees Celsius. Yet, these tiny differences are profound. They represent quantum fluctuations from the universe's earliest moments, stretched and amplified by cosmic inflation. These fluctuations are the result of tiny density differences in the primordial plasma. Slightly denser regions had slightly higher gravity, pulling in more matter and becoming even denser. Over time, these regions grew, eventually collapsing under their own gravity to form the large-scale structures we see today. Without these fluctuations, the universe would be a featureless expanse, devoid of the complexity and diversity we observe. The significance of these fluctuations cannot be overstated. They provide a wealth of information about the universe's composition, shape, and destiny. By studying the patterns and magnitudes of these fluctuations, scientists can determine the density of dark matter, the curvature of space, and the rate of the universe's expansion. They offer a window into the universe's past, present, and future. The fluctuations also confirm the standard cosmological model, providing strong evidence for inflation and the Big Bang theory. They are a testament to the power of the scientific method, revealing the universe's deepest secrets through careful observation and analysis. The CMB and the shape of the universe. The cosmic microwave background, CMB, radiation is a faint glow that permeates the entire universe, a remnant from the early stages of cosmic evolution. This ancient light, released when the universe was just 380 years old, carries crucial information about the shape and structure of the cosmos. By studying the CMB, scientists can infer the geometry of the universe, much like reading the rings of a tree to understand its growth and age. The CMB's temperature fluctuations, measured with exquisite precision by satellites like WMAP and Planck, provide a snapshot of the universe's infancy, revealing clues about its overall shape. The shape of the universe is a fundamental aspect of cosmology, determining its ultimate fate. The CMB data suggests that the universe is flat, or very nearly so, meaning that the sum of the angles in a triangle adds up to 180 degrees, as in Euclidean geometry. This flatness implies that the universe will expand forever, albeit at an accelerating rate due to dark energy. The CMB's uniformity across the sky supports this conclusion, as any significant curvature would distort the pattern of temperature fluctuations. This flatness is a critical piece of the cosmological puzzle, guiding our understanding of the universe's structure and evolution. The CMB's role in shaping our understanding of the universe's geometry cannot be overstated. By analyzing the patterns of temperature variations, scientists can deduce the density of matter and energy in the universe. These measurements have led to the discovery of dark matter and dark energy, which together make up about 95% of the universe's total energy density. The CMB's data also helps constrain the possible shapes of the universe, ruling out closed, spherical, or open, hyperbolic geometries. This information is vital for constructing accurate models of the universe's past, present, and future. The CMB, in essence, serves as a cosmic blueprint, revealing the underlying structure of the cosmos with remarkable clarity. The CMB and dark matter. The cosmic microwave background, CMB, is the oldest light in the universe, a faint glow that has traveled for nearly 13.8 billion years to reach us. It is a snapshot of the universe when it was just 380 years old, a time before stars and galaxies formed. This ancient light is remarkably uniform, with tiny temperature fluctuations that provide a wealth of information about the early universe. Among the most intriguing insights is the role the CMB plays in our understanding of dark matter, the mysterious, invisible substance that makes up about 27% of the universe's mass energy content. The CMB's uniformity is a puzzle, a cosmic enigma that demands explanation. The tiny temperature fluctuations, just a few parts in 100, are the seeds of the large-scale structure we see today. These fluctuations are thought to be caused by the gravitational influence of dark matter. Dark matter, unlike ordinary matter, does not emit, absorb, or reflect light, making it invisible to telescopes. Yet, its gravitational effects are undeniable. The CMB's temperature fluctuations provide a crucial window into the distribution and behavior of dark matter in the early universe. By studying these fluctuations, scientists can infer the presence and properties of dark matter, even though it remains unseen. The interplay between the CMB and dark matter is a dance of cosmic proportions. Dark matter's gravitational pull affects the way ordinary matter clumps together, influencing the formation of the first stars and galaxies. The CMB's temperature fluctuations are a direct result of this gravitational tug-of-war. Regions with slightly more dark matter exert a stronger gravitational pull, drawing in more ordinary matter and causing slight increases in temperature. Conversely, regions with less dark matter have less gravitational pull, resulting in slightly cooler areas. This intricate pattern, etched into the CMB, offers a unique opportunity to study dark matter's role in the universe's evolution. The CMB's significance extends beyond its role in understanding dark matter. It is a treasure trove of information about the universe's composition, geometry, and evolution. By analyzing the CMB, scientists can determine the universe's density, the nature of dark energy, and the conditions that prevailed during the first moments of creation. The CMB is, in many ways, a cosmic fossil, a relic from a time when the universe was far hotter and denser than it is today. Its study has revolutionized our understanding of the cosmos, providing a glimpse into the very fabric of reality. The CMB and dark matter together paint a picture of a universe that is both familiar and profoundly mysterious, a tapestry woven with the threads of visible and invisible matter, all set against the backdrop of the cosmic microwave background. The CMB and dark energy. The cosmic microwave background, CMB, is the oldest light in the universe, a faint glow that permeates all of space, carrying with it the echoes of the Big Bang. This relic radiation, discovered accidentally in 1965, has been instrumental in shaping our understanding of cosmology. Among its many revelations, the CMB has provided crucial insights into the mysterious force known as dark energy, which is driving the accelerated expansion of the universe. The CMB is remarkably uniform, with tiny temperature fluctuations that reveal the seeds of the large-scale structure we see today. These fluctuations, measured with exquisite precision by satellites like WMAP and Planck, offer a snapshot of the universe when it was just 380 years old. By analyzing these patterns, cosmologists can infer the composition and dynamics of the early universe. One of the most startling discoveries from these studies is the evidence for dark energy, a mysterious component that makes up about 68% of the universe's energy density. Its presence is inferred from the observation that the expansion of the universe is accelerating, a finding that was recognized with the 2011 Nobel Prize in Physics. Dark energy's influence on the CMB is subtle but profound. It affects the large-scale geometry of the universe, which in turn influences the patterns of temperature fluctuations in the CMB. By measuring these patterns, scientists can constrain the properties of dark energy. For instance, the CMB data suggests that dark energy behaves like a cosmological constant, a form of energy inherent to space itself, as proposed by Einstein. This constant energy density drives the accelerated expansion, stretching the fabric of space and time. The interplay between the CMB and dark energy provides a unique window into the fundamental nature of the cosmos, revealing how the earliest moments of the universe are connected to its ultimate fate. The study of the CMB and dark energy is an ongoing endeavor, with each new observation refining our understanding. Future missions, such as the proposed CMB S4 experiment, aim to measure the CMB with even greater precision, potentially uncovering new physics beyond the standard cosmological model. The CMB, as the echo of creation, continues to be a goldmine of information, guiding us through the enigmatic landscape of dark energy and the accelerating universe. Its study not only deepens our knowledge of the cosmos, but also challenges our understanding of the fundamental forces and particles that govern it. The CMB and the accelerating universe. The cosmic microwave background, CMB, radiation is the oldest light in the universe, a faint glow that has traveled for nearly 13.8 billion years since the dawn of time. It is the afterglow of the Big Bang, a snapshot of the universe when it was still in its infancy, around 380 years old. This ancient light is remarkably uniform, with tiny temperature fluctuations that provide a wealth of information about the early universe and its evolution. Among the most profound insights gleaned from the CMB is its role in revealing the accelerating expansion of the universe, a discovery that has reshaped our understanding of cosmology. The CMB's role in uncovering the accelerating universe begins with its role as a standard ruler. By measuring the pattern of temperature fluctuations in the CMB, scientists can infer the geometry and composition of the universe. These measurements have shown that the universe is not only expanding, but doing so at an accelerating rate. This acceleration is attributed to dark energy, a mysterious force that makes up about 68% of the universe's energy density. The CMB's data, combined with observations of distant supernovae, has provided compelling evidence for this acceleration, leading to the Nobel Prize in Physics in 2011. The implications of an accelerating universe are profound. It suggests that the fate of the universe is one of eternal expansion, with galaxies moving away from each other at an ever-increasing pace. This has significant consequences for the ultimate fate of the cosmos, potentially leading to a big freeze scenario where the universe becomes increasingly cold and empty. The CMB's role in this discovery highlights its importance as a tool for understanding the fundamental nature of the universe. It serves as a cosmic time machine, offering a glimpse into the early universe and providing clues about its ultimate destiny. Through the CMB, scientists continue to unravel the mysteries of the cosmos, pushing the boundaries of our knowledge and deepening our appreciation for the vast and complex universe in which we live. The CMB and the multiverse hypothesis. The cosmic microwave background, CMB, radiation is the oldest light in the universe, a faint glow that has traveled for nearly 13.8 billion years since the dawn of time. This relic radiation, discovered accidentally in 1965, provides a snapshot of the universe when it was just 380 years old, a mere infant in cosmic terms. The CMB is remarkably uniform, with tiny temperature fluctuations, just a few parts in 100, revealing the seeds of the large-scale structure we see today. These fluctuations are the echoes of quantum fluctuations stretched to cosmic scales during a period of rapid expansion known as inflation. The CMB's uniformity is both a puzzle and a clue. It suggests that the universe was once in thermal equilibrium, with all parts in intimate contact. But how did such distant regions communicate to achieve this uniformity? Inflation offers an explanation. A brief period of exponential expansion smoothed out any irregularities, making the universe look the same in all directions. Yet, this same inflationary theory also opens the door to a more radical idea, the multiverse hypothesis. If inflation is a generic feature of quantum fields, it might not have stopped in our universe. Instead, it could be an ongoing process, spawning an infinite number of bubble universes, each with its own fields and interactions. The multiverse hypothesis suggests that our universe is but one in a vast ensemble, each with potentially different physical laws and constants. The CMB could hold clues to this cosmic multiplicity. Some theories propose that collisions between bubble universes might leave imprints on the CMB, subtle but detectable patterns that deviate from the expected statistical distribution. These imprints, if found, would be nothing short of revolutionary, providing direct evidence for the existence of other universes. While no such signatures have been conclusively detected yet, the search continues, driven by the tantalizing possibility of peering beyond our cosmic horizon. The CMB's role in probing the multiverse hypothesis is not just speculative. It is a concrete avenue for testing one of the most profound ideas in modern cosmology. By analyzing the CMB's polarization patterns, scientists hope to uncover evidence of gravitational waves from the early universe, which could also hint at the multiverse. The Planck satellite and other advanced instruments have already provided unprecedented data, but the quest for definitive proof is far from over. Each new observation brings us closer to understanding whether our universe is one of many or a singular, isolated entity in the vast expanse of existence. The CMB, in its quiet, persistent glow, remains our most powerful tool in this cosmic detective story. The CMB and inflationary theory. The universe, in its infancy, was a hot, dense soup of particles and radiation. As it expanded and cooled, this primordial plasma began to release light, creating a cosmic fog that permeated the entire universe. This light, now stretched to microwave wavelengths by the expansion of the universe, is what we detect today as the cosmic microwave background, CMB. It's the oldest light we can see, a snapshot of the universe when it was just 380 years old. The CMB is remarkably uniform, with tiny temperature fluctuations that provide a wealth of information about the early universe. Inflationary theory posits that the universe underwent a period of exponential expansion, growing from a subatomic size to a size larger than a grapefruit in less than a trillionth of a second. This rapid expansion would have smoothed out any initial irregularities, making the universe incredibly uniform. It also would have generated quantum fluctuations, tiny variations that would later grow under gravity's influence to form the large-scale structure of the universe we see today. These fluctuations are imprinted on the CMB, providing a crucial test for inflationary theory. The CMB's temperature fluctuations are incredibly small, only about 1 part in 100 zero. Yet, these tiny variations hold a wealth of information. They provide a snapshot of the universe's density fluctuations at the time of recombination, when electrons and protons first combined to form neutral hydrogen atoms. These fluctuations are the seeds of all the structure we see today, from galaxies to galaxy clusters. By studying the CMB, scientists can learn about the composition, shape, and evolution of the universe. It's like having a baby picture of the cosmos, holding clues about its growth and development. The CMB also provides a test for inflationary theory. The theory predicts a specific pattern of temperature fluctuations, with a particular distribution of sizes and strengths. Observations of the CMB have largely confirmed these predictions, providing strong support for inflationary theory. Moreover, the CMB's uniformity is exactly what inflationary theory predicts. Without inflation, the universe would be much more lumpy and irregular. The CMB, then, is not just a relic of the early universe. It's also a crucial piece of evidence supporting our current understanding of the universe's origin and evolution. The CMB and the future of cosmology. The cosmic microwave background, CMB, radiation is the oldest light in the universe, a faint glow that has traveled for nearly 13.8 billion years since the dawn of time. It is the afterglow of the Big Bang, a remnant of the intense heat and energy that filled the universe in its infancy. This relic radiation is remarkably uniform, with tiny temperature fluctuations that provide a snapshot of the universe when it was just 380 years old. These fluctuations are the seeds of the large-scale structure we see today, the cosmic blueprint that gave rise to galaxies, stars, and ultimately, life. The CMB is more than a historical artifact. It is a treasure trove of information that cosmologists are still unraveling. By studying its properties, scientists can probe the fundamental nature of the universe, testing theories about its origin, composition, and ultimate fate. The CMB's discovery in 1965 was a watershed moment in cosmology, providing strong evidence for the Big Bang theory. Since then, missions like COBE, WMAP, and Planck have mapped the CMB with increasing precision, revealing intricate details about the early universe. These observations have allowed cosmologists to refine their models, constraining the values of key parameters such as the density of dark matter, the rate of cosmic expansion, and the nature of dark energy. Looking ahead, the CMB holds even greater promise for the future of cosmology. Next-generation experiments, both on the ground and in space, aim to measure the CMB with unprecedented accuracy. These include ground-based telescopes like the Simons Observatory and the CMB S4 experiment, as well as proposed space missions that could further push the boundaries of our understanding. One of the most exciting prospects is the search for primordial gravitational waves, ripples in space-time that could provide direct evidence of inflation, the rapid expansion of the universe in its first fraction of a second. Detecting these waves would be a monumental achievement, offering a window into the physics of the very early universe and potentially unifying quantum mechanics with general relativity. Moreover, the CMB can serve as a backdrop for studying other cosmic phenomena. For instance, the distortion of the CMB by intervening matter can reveal the distribution of dark matter and the large-scale structure of the universe. Additionally, the CMB can be used to probe the nature of neutrinos, elusive particles that play a crucial role in the evolution of the cosmos. By analyzing the subtle imprints left by these particles on the CMB, scientists can infer their properties and interactions, shedding light on one of the most enigmatic components of the universe. In this way, the CMB is not just a relic of the past, but a dynamic tool for exploring the present and future of cosmology. Its study continues to push the boundaries of our knowledge, driving innovation and discovery in the quest to understand the universe in which we live. The CMB's impact on our understanding of the universe. The universe, in its vast expanse, has always been a canvas of mysteries, and the cosmic microwave background, CMB, is one of its most profound brushstrokes. This faint, almost imperceptible glow, permeating every corner of the cosmos, is the afterglow of the Big Bang, a relic from a time when the universe was a mere 380 years old. It's a snapshot of the infant universe, a cosmic baby photo, if you will, frozen in time and space. The CMB's discovery in 1965 was a watershed moment, but its true impact on our understanding of the universe has been unfolding ever since, revealing secrets about the cosmos' composition, shape, and ultimate fate. Picture this: the universe as a vast, echoing chamber. The CMB is the echo of creation, a whisper from the past that has traveled billions of years to reach us. By studying its patterns and fluctuations, scientists have gleaned invaluable insights. For instance, the CMB's uniformity has provided robust evidence for the Big Bang theory, while its tiny fluctuations have offered clues about the distribution of matter and energy in the early universe. These fluctuations, known as anisotropies, are like the seeds from which galaxies and galaxy clusters grew. By mapping these patterns, scientists have been able to reconstruct the universe's evolutionary timeline, much like archaeologists piecing together a civilization's history from pottery shards. The CMB has also been instrumental in shaping our understanding of the universe's composition. It has revealed that the universe is predominantly made up of dark energy and dark matter, mysterious entities that we can't see but can infer from their gravitational effects. The CMB's data has allowed scientists to estimate the proportions of these components, with dark energy accounting for about 68% of the universe's energy density, dark matter making up around 27%, and the rest, everything we can see and interact with, constituting a mere 5%. This cosmic recipe has profound implications for the universe's ultimate fate, suggesting it will expand forever, growing colder and darker. Moreover, the CMB has helped us understand the universe's geometry. By analyzing its patterns, scientists have found that the universe is flat, or very nearly so, within the limits of our current measurements. This means that, on the largest scales, the universe's geometry obeys Euclidean principles. Parallel lines never meet, and the angles of a triangle add up to 180 degrees. This finding has significant implications for our understanding of the universe's origin and evolution, supporting the idea that the universe underwent a period of rapid expansion known as inflation shortly after the Big Bang. The CMB, in all its subtlety, continues to be a goldmine of information, reshaping our understanding of the cosmos and our place within it. The CMB and ongoing research. The cosmic microwave background, CMB, radiation is the oldest light in the universe, a relic from the time when the cosmos was just 380 years old. It permeates the entire universe, providing a snapshot of the early universe's conditions. Ongoing research into the CMB is like peeling back the layers of a cosmic onion, revealing intricate details about the universe's birth, evolution, and ultimate fate. Scientists are using advanced technologies to measure the CMB's temperature fluctuations with unprecedented precision. These fluctuations, though minuscule, encode a wealth of information about the universe's density, composition, and the seeds of large-scale structures we see today. One of the most exciting areas of CMB research is the hunt for primordial gravitational waves. These waves, if detected, would provide direct evidence of cosmic inflation, the rapid expansion of the universe in its first trillionth of a second. By studying the unique polarization patterns imprinted on the CMB by these waves, researchers hope to uncover clues about the physics of the very early universe. Experiments like the BICEP/Keck array at the South Pole and the Simons Observatory in Chile are at the forefront of this quest. They are designed to measure the CMB's polarization with extreme sensitivity, pushing the boundaries of our understanding of the cosmos. Moreover, the CMB serves as a backlight for the entire universe, allowing scientists to study the distribution of matter and energy along its line of sight. By observing how galaxies and galaxy clusters distort the CMB through a phenomenon called the Sunyaev-Zel'dovich effect, researchers can map the universe's large-scale structure and track its growth over time. This provides valuable insights into the nature of dark matter and dark energy, the mysterious components that dominate the universe's energy budget. Upcoming missions like the European Space Agency's Euclid satellite and NASA's SphereX mission aim to leverage the CMB's unique properties to shed light on these enigmatic components. In addition to probing the early universe, the CMB is a treasure trove for studying fundamental physics. It offers a unique laboratory for testing theories of gravity, particle physics, and even the quantum nature of space-time. For instance, the CMB's polarization patterns can reveal the presence of exotic particles or interactions that left their imprint on the early universe. Furthermore, the CMB's blackbody spectrum, which is the most perfect blackbody spectrum ever observed, provides a stringent test of the standard model of particle physics. Any deviations from the expected spectrum could hint at new physics beyond our current understanding. Thus, ongoing research into the CMB is not just about understanding the universe's past, but also about exploring the frontiers of physics. The CMB, a window into the past. The universe, in its infancy, was a hot, dense soup of particles and radiation. About 380 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. This allowed light to travel freely for the first time, creating a cosmic fog of radiation that we now detect as the cosmic microwave background, CMB. It's the oldest light in the universe, a snapshot of the cosmos when it was just a baby. This ancient light, stretched and cooled by the expansion of the universe, now washes over us as a faint glow in the microwave part of the spectrum, nearly uniform in all directions. The CMB is a treasure trove of information, a cosmic time capsule that offers a glimpse into the early universe. It provides a wealth of data about the composition, shape, and evolution of the universe. Tiny fluctuations in the CMB's temperature and polarization patterns, detected by instruments like the Planck satellite, reveal the seeds of the large-scale structure we see today. These fluctuations are the imprints of quantum fluctuations from the very early universe, amplified by cosmic inflation. They are the blueprints of the galaxies, stars, and clusters that would form hundreds of millions of years later. By studying these patterns, scientists can infer the density of matter and dark matter, the nature of dark energy, and the geometry of the universe. The CMB also serves as a backdrop for studying the large-scale structure of the universe. It's a cosmic ruler, allowing astronomers to measure the distances and distribution of galaxies. The patterns in the CMB can be used to test theories of cosmic inflation, the rapid expansion of the universe in its first tiny fraction of a second. They can also probe the nature of dark energy, the mysterious force driving the accelerated expansion of the universe today. Moreover, the CMB provides a unique laboratory for studying the physics of the early universe, including the behavior of neutrinos and the nature of dark matter. It's a window into a time when the universe was far hotter and denser than it is today, offering clues about the fundamental laws of physics that govern our cosmos. The CMB, a tool for the future. The cosmic microwave background, CMB, is a relic radiation from the early universe, a faint glow that permeates all of space. It is the oldest light we can observe, originating just 380 years after the Big Bang. This ancient light, stretched and cooled by the expansion of the universe, now bathes the cosmos in a nearly uniform glow, with a temperature of just 2.7 Kelvin above absolute zero. The CMB is not just a remnant of the past. It is a powerful tool for understanding the present and future of the universe. The CMB provides a snapshot of the universe in its infancy, offering clues about its composition, structure, and evolution. By studying the tiny fluctuations in the CMB's temperature and polarization, scientists can infer the distribution of matter and energy in the early universe. These fluctuations, known as anisotropies, are the seeds of the large-scale structures we see today: galaxies, clusters, and superclusters. The CMB also holds information about the nature of dark matter and dark energy, the mysterious components that dominate the universe's energy budget. By analyzing the CMB, scientists can constrain the properties of these elusive substances, shedding light on their role in the universe's expansion and ultimate fate. Looking ahead, the CMB will continue to be a vital tool for probing the fundamental physics of the universe. Future missions, such as the proposed CMB Stage 4 (CMB S4) experiment, aim to measure the CMB with unprecedented precision. These measurements will help scientists test theories of inflation, the rapid expansion of the universe in its earliest moments. Inflationary models predict specific patterns in the CMB's polarization, and detecting these patterns could provide strong evidence for these theories. Additionally, the CMB can be used to study gravitational waves, ripples in spacetime caused by massive, accelerating objects. By measuring the imprint of these waves on the CMB, scientists can probe the dynamics of the early universe and the nature of gravity itself. The CMB is also a valuable resource for studying the distribution of matter in the universe. As light from distant galaxies and quasars travels through the universe, it interacts with the CMB, imprinting information about the intervening matter. By analyzing these interactions, scientists can map the large-scale structure of the universe and study the growth of cosmic voids and filaments. This information is crucial for understanding the role of dark energy in accelerating the universe's expansion. Furthermore, the CMB can be used to study the Sunyaev-Zeldovich effect, a distortion of the CMB caused by high-energy electrons in galaxy clusters. By measuring this effect, scientists can infer the properties of these clusters and the distribution of hot gas within them. This information is essential for understanding the formation and evolution of galaxy clusters, the largest gravitationally bound structures in the universe. As we draw the curtains on our journey through the cosmic microwave background, let's take a moment to absorb the sheer magnitude of what we've explored. We've dived into the afterglow of the Big Bang, a faint hum echoing through the universe, carrying secrets of our cosmic origins. This ancient light, stretching across the vast expanse of space, has revealed the universe's infant structure, its composition, and its ultimate fate. Imagine, if you will, standing on a cosmic shore, listening to the whispers of creation. Each ripple in the CMB is a story, a testament to the universe's incredible journey from a hot, dense state to the vast, cool cosmos we see today. It's a reminder that we are not just observers, but participants in this grand cosmic narrative. So what's next? The cosmos is vast, and our exploration has only just begun. Join us in our next adventure as we continue to unravel the mysteries of the universe. Subscribe, hit the bell icon, and let's embark on this journey together. The cosmos awaits, and with each discovery, we inch closer to understanding our place in this magnificent universe. Until then, keep looking up, keep wondering, and remember, the universe is not just out there. It's within us, in every atom, every thought, every dream.